Hey guys, how's it going? I'm pretty excited to introduce the topic of naive bias in today's session, and hopefully we'll take out some of the myths around it, some of the confusions around it to get some clarity about it. So let's deep dive into it. So the naive bias, the introduction is the classification technique, and the classification is done based on the features supplied, and it's a supervised algorithm. And the typical applications include spam filters, document classifications. Believe me, a lot of document classification engines use naive bias because it performs well and it's very scalable and performant. And naive, the name naive comes from the assumption that algorithm holds the features are independent of each other. That means the relationships between the features are not even considered in the evaluation of the algorithm, and it's primarily based on the probabilistic approach. It can be real-time, quick, and scalable, as I mentioned earlier. Um, it's time to introduce the conditional probability. And the probability of, maybe if we take a look at the probability of flipping a fair coin, the probability of getting a head or tail is probably 50%. It's 50%. And how about picking a queen given the card is a diamond? So the given the card is a diamond, there's a condition that is crucial here because it restricts our options. Now, instead of taking a deck of 52 cards and evaluating the probability of picking a queen, now we're restricted only to the 13 cards of diamond, and in those 13 cards, we're picking a queen, and it will be 1 by 13 and not 1 by 52. So this is a classic case of conditional probability. Why we say that? And conditional probability is one of the important concepts of Bayes' theorem. So Bayes' theorem states that the probability of hypothesis given an evidence is equal to the multiplication of probability of evidence given the hypothesis and probability of hypothesis. It's all normalized by the probability of evidence. Hang on, we will decode all those terms as we go along. And there are the below or some of the terms that we need to be familiar about, and we will be exploring that in future slides as well. And posterior probability is something that the Bayes theorem gives us. It's the probability given the evidence, and the prior probability is something that we know before we even were provided with evidence. And likelihood is probability of the evidence happening given the hypothesis. So, and probability that is the denominator is to normalize the measurements across the classifications and across the various possibilities. Let's make that concrete with an example. So let's say we have a deck of cards. We wish to find out the probability of picking a random card, which is a king, given that it is a face card. So now let's try to identify the components here. What's the probability of picking a king? So we need to pick up a king, and without considering the condition that is being given to us, it will be 4 out of 52, as there are 4 kings in the deck of cards. And what is the probability of picking a face given that it is a king? Because all the kings cards are face cards, so it will be 1. It's deterministic. And what is the probability of face? Is there are 12 face cards out of 52 cards, so 3 face cards per suit, and there are 4 suits in total. So plugging it all these things in the equation, so our matter of interest is probability of king getting a king given it is a face card. So probability of getting a king, which is a prior probability, and multiplied with the probability of face giving a king, which is the reverse of what the posterior probability is. And then at the denominator we have the probability of face, which is to normalize the classification, normalize the measurements across the classification. If we plug everything in, we get 1/3. We can directly find out the answer for this question. So if we say probability of getting a king given that it is a face card would be the face card, there are 12 face cards and there are 4 kings, 4 by 12 will be 1/3. So this is to cross check like how the base formula can be used to find out um, the probability of occurrence of something in terms of hypothesis given an evidence. And let's take another example which is more concrete and kind of more complex and real world. So let's say we have a lab test, and the lab is claiming that the results are 99% accurate, and if you have the disease, they will give the test positive 99% of the time. If you don't have the disease, they will test negative 99% of the time. And the probability of the occurrence of disease generally is 3% of all the people, and test gives positive result. So what is the probability that the person who's already going is actually having the disease? So this is once again the hypothesis and evidence-based question. So if we go here, we know that the probability of people suffering from the disease in general, this is a prior probability without even knowing whether the test results are positive or not, is 3%. The probability that the test gives the positive results and the patient has the disease as they claim by the lab is 99%. That's probability of given the patient has disease and the test is positive. And the people not suffering from the disease generally is 97%, which is because the people suffering from the disease is 3%, and 100 minus 3 it is. The probability that the test gives the positive result and patient does not have the disease at all would be, it's like 1% because it's 100 minus 99%. Now, we know the probability of patient probability of test getting the positive result given the patient is having the disease, which is 99% into, and the probability of people suffering from the disease, which is 3%, divided by the probability of getting the positive results. What involves in getting the positive result is probability of patient having the disease given the positive result, probability of patient not having the disease given the positive result. So when we plug in all those calculated values in here, we get approximately 75% chances are there that the patient is actually suffering from the disease. So if you look at the initial assumption as claimed by the lab, it is 99% that the tests are accurate. But after getting into the Bayes theorem and plugging in the values that we know of, the probability of the person actually having the disease is reduced to 75%. It is majorly impacted by the prior probability and the likelihood, and also the different cases that we are evaluating, like the patient, the probability that gives positive result when the patient has the disease or patient does not have the disease. So this is more of a realistic value, and it is way deviated from like what the labs claim to be. It's 99%. So this is where the Bayes theorem is really helpful in order to evaluate based on what we know and what is the likelihood of particular hypothesis being true. So overall, so got this one advantages. It's fast, highly scalable. This can be used for binary and multi-class classifications as well. It's a popular choice for spam emails, and can be easily trained because it's based on the probabilities, and most of the time the likelihood and the prior probabilities are already calculated, and all the naive Bayes theorem needs to plug it in is to put in those values and find out the maximum likelihood probability. Disadvantages, it considers, as I said, all the features to be unrelated, so it cannot learn from the relationships between the features. So so irrespective of that, it is assumed that it is proven to be very effective, even in terms of features having certain relations. Some of the features having certain relationships are even performing well in naive Bayes classification. It's able to classify that as well. So Hope you have a good understanding about what naive bias is, and hope to see you guys again. Happy learning.